previous was wrong. Okay, thank you, Uma. My name is Aitor. I'm a PhD student here at the University of Valladolid at the Forest Modeling Group. And the topic I'm going to talk today is machine learning alternatives to assess individual tree mortality, a performance comparison. And I'm going to start in the same way as Farouk. Let's start thinking into a forest. Forest seems really static ecosystems, but they are really dynamic. If we think on trees, just on trees, they are continuously growing. New trees are appearing by regeneration, and other trees are dying. And that's the topic I'm going to talk today. All of that dynamics are studied under a sector of forestry called forest modeling. So basically, forest modeling creates an abstract idea of our forest based on different measurements like diameter and height of the trees. We create that picture, and with that picture, we are able to predict what will happen in our forest under different conditions. So, for instance, here I show you what will happen in a forest under different managements. But forest modeling has some weaknesses, and one of the weaknesses of forest modeling is to predict the tree mortality, the individual tree mortality. We already know that some processes are behind that tree mortality, like, for instance, the drought periods or the competition of the other trees, but that process is still difficult to predict at individual level, and is more difficult even if we want to take into account the effects of the climate change. And even more, if we include some random effects that can appear or not on that process, like wildfires or pathogens, as Farouk was talking before. So, knowing that, we said, okay, well, to assess that problem about tree mortality, what's the better tool to assess that problem? And here is when machine learning comes in. Machine learning, for sure you hear about that, is like let's say a part of artificial intelligence, and is made by different algorithms that are able to find patterns on your data, and with that patterns, able to predict what will happen under different situations. So basically, it's statistics, but with a cool name, with a smart name. And it works like this. We have some input, for instance, some fruits. We extract some features of our input, like, for instance, the color of the fruits. We classify them using different algorithms, and as a result, we have our input perfectly classified, in that case, in different fruits. So what we did was exactly the same, but with trees. We have trees that we know they are alive or dead, and let's start for this. For our data, we take different experimental plots of Norway spruce, all of them located in Germany, in a southern region of Bavaria. Maybe all of you know about that region because there is the place where is celebrated the Oktoberfest, and that's the reason why I moved there, to study that tree mortality stuff. You know? So, okay, we have our data, alive and dead trees, and then we extract some features about that trees. To do that, we focus just on the closest neighborhood of each tree, the places inside that circle around the tree. And there we calculate different variables like competition, growth, climate, and so on. And for those trees in the border, like this one, we use like a correction factor to correct that variables. So great, we have our data and we have our variables, and now is where the algorithms come in. As reference on that topic, logistic binomial regression is the traditional methodology applied to assess tree mortality. So we wanted to compare the performance of that methodology to other algorithms like decision trees, random forest, KNN, naive badges, and support vector machine. I have no time to explain how they work in deep, but basically they are able to find patterns on our data on different ways. So we wanted to compare them and provide some guidelines to next users that want to fit models of tree mortality under different situations. So we plan different case studies and compare them under different case studies. So here are some of the results, and all of the results looks in the same way. In the y-axis, we have the accuracy of the predictions. On the top, the better accuracy. And in the x-axis, we have different cases studies I will explain on each graph. And on one color, we have different algorithms, and just please focus on the one which is on the top, always that dark green, which is random forest. So in the first case study, we said, okay, we have our database is around 80,000 trees, and we said, okay, what happens? Do the models perform different under different sizes of our data set? So we split the data set in 3 different sizes, and we found that random forest is the algorithm that performs better in all the situations. Then we said, okay, and maybe they are affected by the number of variables we include in the model. So we said for different degrees, or where we include more variables on each time to the model, and we found that, again, random forest is the algorithm that performs better on each condition. And when we have more variables, all the algorithms predict better tree mortality. So, okay, the first winner under all the size of the data set and number of variables is random forest. And then we said, okay, we have a lot of plots. Some plots were measured between 3 and 5 times, and for another plot we have even 6 inventories, 7, or even more. Maybe there is one algorithm that is able to find different patterns if we provide more inventories of the same plot. And the answer was no, but in all the cases, again, random forest is the winner, is the one that reached the better accuracy on the predictions. And then we said, okay, we also have different thinning grades. We have some control plots where no management was applied, and others managed by thinning from above and thinning from below. And so we split our data set in that 3 groups, and we found that the accuracy for all the algorithms is better on the control plots because that structures are not altered by human actions. And in all the cases, again, random forest reach the better prediction accuracy. So winner again, random forest. So then we plan the last case study. What happens if we fit a model with the control data and we apply this model to one plot under different management? So we did all the combinations, and we found that in all the cases the accuracy of the predictions decreased, but in that cases random forest is the one that decreased the most the accuracy. And among the other algorithms, maybe the most robust is logistic regression, the traditional approach. So as a summary of all this work, we already know that tree mortality is a process difficult to assess. It includes some randomness that we will never be able to predict, like wildfires or affection by pathogens. And we found that random forest is a good approach. The results are better than other algorithms, but it has some weaknesses when we don't use when we don't apply the models to the correct data. And logistic regression, the traditional approach, reach always good accuracy on the predictions, a bit lower than random forest, but is more secure when we doesn't know which use will have our model, when we doesn't know which data will be used with that model. And that's all from my side. Thank you for your attention, for the organizers.